So hey guys, this is Ayush Singh, and in this video what I'm going to do is that I'll make you familiar with the non-linear decision boundaries of support vector machines, and also we'll take a look at the kernels and a similarity function. Till now we are dealing with only the linear boundaries or linear separable boundaries in support vector machine, and we are just drawing a straight line and we are classifying positive and the negative examples. That just separates. This means the positive, this means the positive, and this means the negative examples. So in our previous end of some of the previous videos, this is the positive, this is my positive, and this is my negative. And what we are doing just drawing a line, and we are separating at a large margin, and we are good to go. But either there are the non-linear boundaries in SVMs that uses complex functions to build a non-linear boundaries. So that we'll take a look in this video. And the second point is the non-linear boundaries. We will now take a look at that. Okay, so first of all, let's take a look at actually how non-linear boundaries look like. So yeah, yes, black pen. Okay, so these are the negative points. The O here is my negative points, and the cross here is my positive points. And you can see here, if we draw the straight line, you can see here, this is not the good model. This is not the good hypothesis. This is not the good support vector machine decision boundary. Yeah, no. So this will give a very bad prediction, and this model is not the good model at all. So for that, we don't use a linear separable case, we use the complex or non-linear boundaries. So the non-linear boundaries look something like this. It simply means that it separates out from the negative and the positive example by making a non-linear boundaries. And for making a non-linear boundaries, we will go on to deep dive into the maths, and then I will present you to how actually this non-linear boundaries has made. Okay, so this might even give you the exact thing, the non-linear boundaries intuition, actually how non-linear boundaries looks like, and the hypothesis. And the hypothesis of this means non-linear boundaries is something like a complex function. It's the complex function. Okay, this is a very complex function. So this is the non-linear boundaries. Now let's get into the math, and let's draw back. So for that, before going on to that, let's first explore the concept of kernels. Why we use kernels? We use kernels for a non-linear boundary. Sometimes it's called kernel functions or a kernel trick. You might be seeing somebody in the YouTube the kernel trick or a kernel functions. Okay, and in kernels we specify landmarks. We'll talk about the landmarks just in a second. We specify landmarks, and let's denote the landmarks as L1, L2, and L3 all the way down to the Li. Okay, where we usually denote, as I have seen till now, is we usually denote landmark as Li. It is the landmark and the index position. Okay, so if we give our input feature x, then it computes to the new feature. If we give our input feature x, by providing a landmarks, it will give us other new features. And here the new features, let's denote as fi. Okay, we'll talk about how do we compute. how do we compute? Here computation as in happening. So for computing we have our similarity function. To do this, we have our similarity function of x on and some landmark li. And what does that similarity function looks like? Let's take a look at that. So in similarity function, let's denote a feature which is a new feature fi, and here is the similarity of x and a landmark whatever the index position is. And the similarity function looks like exponent minus the norm of x minus li squared upon 2 standard deviation, standard or a sigma squared. Okay, and here sigma is a parameter. Sigma is a parameter of whom? Of this Gaussian kernel. And you might be thinking, hey, wow, what I've told you, a Gaussian kernel. And this whole similarity function known as Gaussian kernel. And this parameter sigma is the parameters of a Gaussian kernel. We can increase or decrease this sigma for that is the parameters for our Gaussian kernel. Okay, this is the name that I have to give to you. Now I think you might be familiar with the similarity function that we give input feature x by similarity function perform some action with the x and the landmark, and it returns the new feature which is fi. Okay, pretty much clear. Now let's go on to the next slide. In the similarity function we can write through n number of examples by a single summation. Okay, so we have written a single summation and xj minus li, again the same thing here, but we have written down the for number of training examples. Okay, just the same thing. But there are a couple of properties of kernels. There are a couple of properties of kernels that you should at least know about that. So let's take a look at the property number 1. And property number 1, if x, here x is approximately or equals to the landmark, if x, let's denote x is approximately equals to the landmark what we have instantiated, then fi would be equals to 1. I will show you the diagram just in a second, but see here that in property number 1, if our x value is approximately equals or near or say at a very close place, then the fi would be equals to 1. And in property number 2, we have if x is far away from li, means landmark. If x, let's denote this is my landmark and x is here, then this and then this fi would be 0. Okay, now there is an hypothesis, so we will take a look at that just in a second. So first of all, let's visualize that example. So first of all, here we have our landmarks. Here I have plotted 3 landmarks, L1, L2 and L3. Let's denote this as a x1, and here the landmark, and here this is so close, so this one here is y equals to 1. If I talk about this is very far away from this, then this is my y equals to 0, and this is also my y equals to 0. And if I take another let's say this is, and then this is so close to this, and this will be y equals to 0. It's totally based upon you can understand the 2 properties. Okay, now each landmark, let's say, gives us hypothesis fi equals to L, f1 equals to L2, L1 f2 equals to L2, f3 equals to L3, all the way down to the fi equals to Li. Okay, and each landmark gives us the hypothesis of our features of the hypothesis, just something like this. And this might be very familiar to you, that this is something called, and here we have not written xi, instead of xi we have written fi, and fi is the similarity of x and Li, and it is equals to the exponents of the norm of xi minus Li upon 2 sigma squared. Okay, and all the way down to the number of features. And let's take theta 0 equals to 0. So don't worry about it, theta 0. That's for simplification, we have taken a lot at that. Okay, and what we will do, we will predict y equals to 1 if this hypothesis is greater than or equals to 0, and if our hypothesis this is smaller than 0, then we will predict y equals to 0. Okay, pretty much clear. Now let's go on to the next slide. Now till now we have studied about the study of the kernels, and I think kernels is very clear to you. Now let's take an example so that we will proceed for a cost function for a non-linear support vector machine. Now we have prepared the decision boundary for our support vector machine. Now it's time to get the parameters theta and use in our model and to get accurate predictions. So first of all, let's see the example here. Here we have f1 equals to similarity of x, then the same thing, and here similarity in all equals to, 1 equals to then exponent of the norm of xi minus Li, L1, whatever it is, upon 2 sigma squared. Okay, and this gives us, all the way down to this gives us the rise of a new feature vector, which is xi. Let's denote xi as an uppercase, and this would be the, let's say f1 equals to similarity of x comma L1. Then we have f2 equals to similarity of x2 L2. Then I have f3 equals to the similarity of x3 comma L3, and all the way down to the f . Okay, and this gives rise us to the feature vector. So note this, we have xi, which is a feature vector of this, and we take x1, x2, x3, x4, x5 to the number for training examples. Okay, and we have taken a look at the feature vector of for proceeding to the cost function for nonlinear boundaries. So to get the parameters theta, we can make use that we studied earlier about the support vector machine's cost function, but with fi instead of xi. Here, let's take a look at a cost function. What we have seen is that all are similar: cost of 1, and a cost of 0. What we have seen, then cost of 1 would be, the diagram is something like that, and the cost of 0 is something like that. Okay, so don't worry about that. This is if you want to get more into detail, please take a look at the cost function for support vector machine. I'll be linking the video down below. Okay, so here we have, instead of xi we have fi, and here fi computes produced by the similarity of x and Li. Okay, and it is exponent of minus the norm of x, let's say xi minus Li upon a norm squared upon 2 sigma squared. And you can do for the whole number of examples whatever you have. Okay, so I have listed on the formula before. You can take a look at that. And see, we use this only, we use the fi only for if we have a non-linear boundaries. And you can do the same for the multi-class classification multi-cluster classification as we have done in a logistic regression. You can take a look at it, and it's the same as a support vector machine. Okay, now I think we have to, this is pretty much clear. At last we just use this cost function j of theta and we get our theta parameters. So I think that's it for this video, and I hope that you had got a very good amount of knowledge from this video. I think this is the second last video. After this video, I'll be bringing up the advice for using an SVM and more about something like how to use SVM, the difference between logistic and a support vector machine, and also SVM parameters. So be sure to check out that last video that I'll be conducting just after this video. So thank you for seeing this video. I'll be catching up in the next video. Till then, bye bye.